So to focus on why does time and throughput improvement matter, it's crucial to our success as an industry in the manufacturing community. And if we're going to be better than our peers, we're going to have to focus on a lot of data. We're going to have to spend a lot of extra time pre-planning and making intentional choices to make sure it's an efficient operation. I think the lack of experience and education in our current manufacturing workforce is a significant problem. We used to have apprenticeship programs, and people could start out in high school and progress slowly and carefully and be mentored by people that had spent their entire career honing their skills. That's gone due to liability issues and other things until we get to the tech school area or an active manufacturing facility. There is no apprenticeship program out there that is global or can serve all manufacturers. So we've got to rethink this, and we've got to start top down. We don't have the time to grow a new set of Class A apprenticed fully machinist over decades. We've got to have people to work in the workforce today and tomorrow and next week. So we've got to give them gifts of controlled processes, well thought out, very well controlled, and implemented properly, top down. So I think there are many metrics that we can observe every day, but I think there's a core group that are like seven key metrics that if we focus on them, we're going to get to the answer much quicker. Manufacturing economics is our guide through this if we're observant on what really makes up the full pie. It's the machine investment, the return on capital. It's the power and overhead, the building, the space, the infrastructure. It's the labor cost, including benefits. It's the cutting tools. It's the tool holders. And it's the time. Time is the most important aspect. We can only affect the time in a big way, so getting more efficient throughput is our number one job. Part cycle time is key. Quite often I'm told that we need your help. The cycle time on this part is taking an hour and a half. And I always chuckle because that's really not the only thing we're going to need to look at. However, if it's planned to take 30 minutes and it takes an hour and a half, everyone can see that that's a problem. What we like to look at more importantly is, we call it chip to chip, from the start of pushing the button go till the part is finished, the operation is finished. But more specifically, we want to look at each tool assembly and the chip to chip time on it. We then want to analyze and see what takes the most time, what operation within that process takes the most time, and let's focus there first. But until we gather all the data, we might assume something and then spend too much time on the wrong part of cycle time. When we look at a manufacturer, we like to look at the metric of what are the materials that you under your roof machine, and we want to bucket them into a percentage. Let's say one, for example, aerospace parts manufacturer, subcontractor to one of the mid-level producers of engines. 80% of their product is titanium, 10% is aluminum, 10% is a heat-resistant superalloy that's nearly unmachinable. That helps us make more clear decisions, because if 80% is titanium, we need to choose more tools and more methods that are more appropriate for titanium and treat the heat-resistant superalloys as a secondary thought, addressing them, but focus more on what's more important under that roof. In addition to the materials machine, we also need to look at the condition. Is it a billet? Is it a bar stock? Is it a casting? Is it a forging? Has it been heat treated? What's the condition of the casting? We need to look at every aspect, because just because you're doing titanium bar and your friend across the street is doing titanium casting, you might not be choosing the right tools or the same tools for each titanium operation. Quite often, the next metric, and usually the first one that we get asked to look at, is the bucket of expendable tooling. I'll hear a statement like, well, we're spending 200 grand a year on drills. And it means nothing to me until we take a full look at all expendable tooling. And then we look at what is the total spend and what makes that up, both in quantity purchased, both in value of each individual item, and then let's put it into the right buckets so that, the top 3 items are end mills, drills, and reamers. Or for another customer, it might be one insert makes up 70% of their spend because they're primarily going to be milling long billets of high temp alloys. And it helps us analyze better to spend the right time on what do we need to do and what do we need to focus on training and assessment first. When looking at another metric is tool assemblies. And are there commonalities in each operation, like say in the milling department or the turning department? Are you using quick change tooling? And if you are using a tool assembly, hopefully pre-staging for setup for the next job you're going to run, are you actually controlling those assemblies? Are you setting them up the same way each time? Are you controlling them so that the next time the job comes up, the tool assembly will be exactly as it was before? And the only way to really do that is to have a tool assembly master and control every aspect and every item within that assembly so that you can have some repeatable processes. And if you improve one, you make one change, and every job that runs that tool will now get the benefit. Quite often I see that there is no tool assembly master. There's some generic general statements, but it's still left up to the operator on the floor or the setup man to make the choice. And I think we're making a big mistake. It should be controlled in a much more finite way so that we can interact and interface and build out that assembly master so that if we have a face mill and it's at a 4-inch gauge length and it's a 45-degree lead and it has a certain grade of insert for, say, titanium, that the programmers always select it as their primary face milling tool, and then the operators know it well, the setup guys know it well, and hopefully your guys in preset are always watching to make sure it's the most valid setup they can do, and it's very controlled. Scrap rate is one of the most overlooked aspects of analyzing what's really happening under a manufacturing floor. You'll hear somebody say, oh my goodness, we had 40 items scrap last week. I think we need to drive the metric deeper. We need to analyze what percent of your overall shipments were scrapped in number of pieces, in which operation, what dollar amount does that equate to as a percent of total revenues produced by the company, and then how often. Is it cyclic? Is it always 2 out of every 100 are scrapped? And we need to really take a hard look at the data so that we are forever going to want to reduce scrap rate. However, we might uncover a machine tool problem, a spindle problem, a tool holder problem, a programming movement problem that's just become accepted, and we're going to learn more by really looking to see where scrap occurs, if at all. We also want to look very intently at the lot size. So when an order is issued for 20 parts, and if that's the only 20 you're ever going to make, we're going to think differently and advise you differently than if you're going to make 2 million of those items this year, and you're going to release them to the shop floor 20 per day. We're going to take a hard look at lot size. So we want to look at average lot size, the largest lot size released to the floor, and then what happens if your best customer says, I need 2 of these tomorrow, and you have to tear down and set up and make only 2. So we're going to have a low, a high, and then we're going to have a median average. And we need to think about that on how we make decisions on the average setup, average number of setups per shift, per day, per week. Some things take 100 hours to make, so you might only have 1 or 2 setups a month. But if you've got 1 or 2 setups a day, it becomes even more critical.